So I've alluded to this idea of coming up with how electrons are hanging out around an atom. Remember, I kind of picked on carbon. I said carbon is atomic number 6. It's got 6 protons if it's neutral. Carbon has 6 electrons. We need to find the homes for those 6 electrons. If we did that, actually, we would be coming up with the electron configuration for carbon's electrons. Okay? Yeah. We are going to focus on electrons as they are hanging out around atoms. They won't always be neutral atoms. They could be ions. But a set of electrons as they're hanging out around the nucleus as those electrons are in their ground state. So all that we've talked about, those rules will apply. Okay. So how you find the lowest possible energy level where electrons can hang out, it actually is applying what we call the lowest n plus L rule. You might be like, that sounds like alphabet soup. Well, we talked about N is the principal energy level, and we talked about L is that angular momentum number, okay? So just to kind of remind you how this works, okay? For our L values, I kind of call it mapping. This is my first semester to call it mapping. Okay, we have S, P, D, and F. Okay, that map to L values of 0, 1, 2, and 3. Okay, you guys had a homework where you guys were going to, I think it went something like this, where, you know, N is equal to, for instance, 2, you know, L is equal to 0, and you guys told me probably that that was, what, the 2s subshell, right? Okay, so for 2s, we could say it has an N plus L value of 2 plus 0 or 2, okay? We could do that for, let's go for 4p. So N is equal to 4, okay? And if it's a p type, L is equal to, what did I say, 1? Okay, so that's 4p, okay? So 4 plus 1 is 5. That is literally that subshell's N plus L value, okay? And what we're going to see is that electrons find homes in the lowest possible energy of a subshell. Okay? All right. So electrons find homes in the lowest N plus L. The lowest N plus L subshell, that's possible. Okay? Yeah. And what we're going to see is subshells fill up, and if this subshell fills up, they're going to go to the next subshell. This subshell fills up, they're going to go to the next subshell. Okay? So I'm going to show you that it's possible that for subshells actually in different principal energy levels that have the same N plus L value. And you're like, well, which one do I go to first, right? Well, you go to the lowest N, and I'll kind of show you. I'm going to introduce you to something, if you haven't seen it before, called the arrow diagram, which kind of gets you down the road to kind of saying, I don't know which N plus L is next. Okay, the arrow diagram will help. If they have they have different subshells with the same N plus L value, you go to the lowest N. Okay. All right. So kind of what I was just describing, kind of this is low energy, this is medium energy, we're going up in energy, that actually kind of leads us to something called the off-bow method of kind of finding homes for electrons, okay? We're going to start here, and then we're going to kind of populate. But we're going to apply the rules that we know about. Specifically, remember any S-type has one subshell, and I'm going to put max number of electrons. We can put 2 electrons in there. Does that make sense? A p-type has actually 3 orbitals. Okay, so maximum number of electrons, 6. D-type, and it's all about oddsies, 5. We max out at 10 electrons. And F-type, 7. Okay, 14 electrons. Okay, so that's what I mean by fill it all. Fill it all. Okay. So, here we go. So I have, we're going to start to look at energy levels for electrons. Now, if an atom has only 1 electron, then actually this says that there's no splitting at the principal energy level. So this is to say for hydrogen hydrogen is like has a proton in it, right? So hydrogen has one electron in an orbital, okay? So this is actually the only case where you see where when n is equal to 2, we know that we can have a 2s and a 2p. And actually, those are the same energy, okay? When n is equal to 3, 3s, 3p, 3d. That only happens for an atom with one electron. Beyond that, which is everything else, okay, what happens in the principal energy levels, they kind of split, okay? So let's look at, for instance, lithium. Now, we're going to run into a few Z is equal to. Now, this is where earlier in the course we talked about the structure of an atom, and we used atomic number, and the symbol for atomic number is Z. So Z is the symbol for the atomic number. What is the atomic number? Number of protons. Actually, you can find lithium on the periodic table. It's got that big old 3 there, okay? So for a lithium atom, okay, when those 3 electrons find homes, see the difference is basically you get a little bit of splitting in the n is equal to 2. The 2s is a lower energy than the 2p. This is more like the onion I drew. For n is equal to 3, we have 3s, 3p, 3d. Okay, just for kicks, let's go ahead and do our first electron configuration. And I'm going to use arrows as electrons. So if I want to find home for 3 electrons, here they go. 1, 2, 3. That's it. See how you go with the lowest possible energy level, fill it up with 2 electrons, and then go to the next subshell, which is a 2s. I'm going to just put 1 in there. Well, let's go to another element, another atom that has more than 1 electron. That would be sodium. If you find sodium on the periodic table, it's going to be the whole number 11. It's atomic number 11. It's got 11 protons in its center. If it's neutral, then we need to find homes for 11 electrons. So here we go. 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and I'll tell you why I kind of did that. I don't know if you caught that, but anyway, I put 6 there in the P. That gives me 10. 1 more, 11. So actually, here in a minute, we're going to see where sodium, that's how the 11 electrons hang out around a neutral sodium atom. That's it. Okay. Now remember the other day, I said when I drew the onion, actually I'm going to have to kind of revisit this and kind of tell you how I lied. Okay? So here's the deal. Let's pick on potassium. Potassium, you have to find homes for 19 electrons, which is not a problem. But potassium, actually, we're going to go into the energy level n is equal to 4. So can you see where this is actually different than what I drew it? And I'm going to show you the arrow diagram that would flesh this out. Okay? The real deal is before you get to 3D, you get to 4S. That's not the way my little onion went, and I'll show you why that is. I'll actually show you why that is now. 4S, the n plus L value for 4S is equal to 4 plus 0, right? We good with that? All right. Well, what's the n plus L value for 3D? 3 plus, help me out, G must be 2. Yep, it maps to 2. 3 plus 2, yep, is equal to 5. So again, the arrow diagram, you're like, how in the heck, and you could use an explicative. Am I supposed to remember that? The arrow diagram will flesh that out. This is to say that 4S is a lower energy than 3D. It just is. It just is. Okay, so before we go away, let's go ahead, and we've been kind of doing the whole finding room for electrons. Let's go ahead and knock out the 19 electrons around potassium. We can do it. Okay, so the first 2 go here. The next 2 go here. The next 6 go here. See, I'm up to actually 10. The next 2 go here. The next 6 go here. Oops, I get sloppy here. All right. So it's like we got 12. Yep. Okay. So 12, I better slow down here. 12, 13, 14. Now I'm going to do something, actually it's called Hoon's rule here in a minute. So I've got 14 electrons. Now I'm going to put the rest in the D. Now watch how I do this. I actually put them in separate boxes first. 14, 15, 16, 17, 18, 19. You'd be like, Mrs. Snipes, why did you do that? And it's called the Hoon's rule. Not the Hoon's rule, but just simply Hoon's rule. I call it the spread out rule. Okay, so that's actually how the 19 electrons around potassium. Did I do something wrong?
The 19th one ended at the 4s.
Oh, thank you. That's like, I lost track. Potassium, oh, it should just be 1.
Yeah.
Thank you, all right. Thank you. Final answer. That adds up to 19.
So it goes to the lowest energy first.
Yep, it goes to lowest energy first. Perfect. Okay. That would be a special potassium atom, wouldn't it? So those are 19 electrons. We got 2 plus 10 is 12, plus another 10 is, oh, wait a minute. Oh, see, sometimes I get out my calculator for this. So we got 10, 12, 14, 16, 18. Okay, I'm convinced. Thanks. All right. All right, so we're just kind of adding on to, speaking the off-bow method, kind of adding on to what we talked about last week, this week. We just started talking about quantum numbers this week. So there are 2 ways to say how electrons are hanging out. Now, kind of what I've showed you is what we call the box and arrow notation. The box represents an orbital, and sometimes the box isn't a box. It's simply a line. Okay, that's where the orbitals are. And the arrows are the electrons. That's the box and arrow notation. Sometimes I call that the hand cramp method because your hand gets tired of drawing all the boxes. Okay, there's actually another way to do that. All right. So here we go. Hydrogen, 1 electron. Dun, dun, dun. Now, that would have what we call the MS value of +1/2, +1/2, because it's visually pointed up, okay? Could you have made it a down arrow? I think so. I don't think there's anything, as long as there's 1 electron there. But helium has 2 electrons. This is what helium looks like. And these are all just increasing by 1 atomic number. Lithium has 3 electrons. I think we looked at this before. There's where the 3 electrons of lithium go. Beryllium, we go ahead and fill up that 2s subshell. There's only 1 orbital in the subshell. We totally fill up the subshell. Okay. So that would be atomic number 4. Atomic number 5 is boron. So here we go. 5. 1, 2, 3, 4, 5. There you go. And these are the next N plus L subshell. Okay, so carbon, actually we get to something a little interesting.
We get crazy.
Remember I said a minute ago incorrectly about the electrons spreading out for potassium. But honestly, it is still called Hoon's rule, so I was correct. So here where we're kind of petering out, adding electrons, when we add that 6th electron, instead of having it share an orbital, it's kind of like kids. You're like, hey, if I got an extra room, it's yours, If you don't have an extra room, they pair up. Okay, so that's actually what electrons do. And they have the same spin, actually. So Hoon's rule, a classic for putting on my next unit exam. Okay. So in so many words, basically the electrons are going to be arranged so that they have the most number of unpaired electrons possible. And with carbon, did you see where I directed them both upwards? Okay, that was the most stable configuration too. They will have the same spin. So you actually have some homework, some homework and potential test questions that ask about kind of paired electrons and unpaired electrons. So, for instance, in the example we looked at with carbon, we ended up with, this 2p subshell, okay? We had an electron there, an electron here. We would call both of those electrons unpaired, okay? Actually, two before carbon, in the case of beryllium, let's pick on beryllium. Oh, by the way, you should never do what I did. You should never have those three and say what they do, and without saying what they are. This is 2p subshell. For beryllium, it petered out in the 2s subshell, okay, and you did one up and one down. Okay, these are paired. Oops, I did it backwards, didn't I? So these are paired. And these are unpaired. All right. So let's apply Hund's rule. After carbon, we pick up an electron with nitrogen, so it looks like this. Okay, and it definitely builds up, So like oxygen kind of piggybacks on nitrogen. For oxygen, we need home for one more electron, and this actually is where we start. Like if your house gets too many kids in it and they need to share a room, that's actually what we do with oxygen. So with oxygen, this is how the electrons are configured. Completely fill the S, completely fill the 1s, completely fill the 2s. When we get to the 2p, we spread them out as possible, and then actually we need to come back and revisit that first orbital. It's the way I think of it. For fluorine, okay, you might have imagined for fluorine, we're going to go ahead and have two orbitals in the 2p subshell completely filled. And we have one lone electron there. One kid who gets his own room. Okay. And then, as some of you know, we'll be talking more about this, and I hope you remember what we talked about with the periodic table. We said that actually we have specific names for certain groups, and that group where neon is in actually are the rare gases. And so the rare gas actually finally goes ahead and totally fills up that 2p subshell. So not only that, but all rare gases have what we call a generic kind of end to their electron configuration. That is what we call generically NS2NP6. Okay, where the superscript 2 for the S means I've got 2 electrons there. The superscript 6 for the P means I've got 6 electrons there. All right. Very good. So that was the hand cramp method. Again, don't ever draw a set of boxes without labeling what subshell that is, whether you do boxes or dashes. Okay, you have to label what that subshell is. This one is a little easier, and it's called spectroscopic notation. Follow the same rules, try to describe the same situation, how electrons are configured. And we're going to actually revisit that first period, or through neon, like we did before. So what you do is you tell the subshell, and in order to tell the subshell, you have to say the principal energy level, in this case 1, and the subshell type, S. So 1s, the superscript is how many electrons there are in that subshell. So 1s, you'll hear me say 1s1, okay, that's what that is. Helium is 1s2. But don't forget that little 2 is a superscript. For lithium, the 3 electrons would be 1s2, 2s1. And this is where I tell students, if you're ever wondering how many electrons you have accommodated with your electron configuration, all you got to do is add up the superscripts. Okay, so we have 3 electrons. And then after lithium, we go to the 4 electrons around beryllium, 1s2, 2s2. I feel like I'm playing bingo or something. And then we go on to boron, the 5 electrons. It goes 1s2, 2s2, 2p1. And then we hop on over to carbon. Okay, and to me, carbon, remember I said Hoon's rule is a big hairy deal with electrons in the same subshell? Remember we said electrons in the same subshell, same principal energy level, they're what we call degenerate orbitals. So, or I should say orbitals in the same subshell are degenerate orbitals. So this, I feel like it loses a little bit of information. So 1s2, 2s2, 2p2. We can't show that those are spreading out. Okay, we just got to. After carbon, we have nitrogen, 7 electrons to accommodate, so 1s2, 2s2, 2p3. Everybody's got their own room. So this is where you just need to kind of be thinking about p subshells have 3 orbitals. How are they going to hang out? Well, they're all going to be spread out. Then we go on to oxygen, 1s2, 2s2, 2p4. Again, just try to kind of, what does the 2p4 mean? Well, you're going to, like we saw a minute ago, you're going to have one room entirely filled, and the other 2 are going to have their own rooms. Then we go on to fluorine, 1s2, 2s2, 2p5. And then we end with neon, 1s2, 2s2, 2p6, our rare gas. Okay, so 2 ways to say how electrons are configured. That all works. One thing we still need to revisit is the lowest n plus L rule. Okay. So what I'm going to draw here is called the arrow diagram, and there's kind of different versions of the arrow diagram. But I'm going to kind of show you how to construct it. If you wanted to construct it on your test, this is what it would look like. So basically, you start out with n is equal to 1. Okay, how many subshells we got? Just 1. So 1s. You line up, n is equal to 2. You line up your s's and your p's. We're going to basically have, almost basically 4 columns here. It's like kind of like, a little bit like playing cards, kind of stacking them. Kind of like playing solitaire. Oh my gosh. So 2s and 2p, n is equal to 3. We start another column, 3s, 3p, 3d, and they all have to line up. The problem with the arrow diagram, what I've seen with students when they draw it for themselves on the test, is they kind of get, it's easy to do, they kind of get them mismatched. N is equal to 4, we pick up the F type. Okay. Now, for all of these other ones, okay, even though there's a G and a H and an I, we pick them up at those principal energy levels. We're not going to be actually finding homes in those subshells as electrons are in their ground state. So you see they're kind of grayed out. So I probably would just stop with that 4th column, F. So where's the arrows, right? If it's an arrow diagram. Well, here are the arrows. They're kind of diagonal, okay? And you're going to see that each diagonal actually, when subshells go, where the arrow goes, all have the same n plus L value. So here we go. Here's our first diagonal. Actually, our first 2 diagonals only pick up 1 subshell. Now, our third diagonal is going to start through the 2p and end through the 3s. Okay. Our 4th diagonal looks like it's going to pick up 3p and 4s. Okay. Our next diagonal, we're going to go 3d, 4p, 5s. Now, like I said, and you can do the math if you want to, but each diagonal actually, each set of subshells on that diagonal have the same n plus L rule, or excuse me, n plus L value. They do. Then we got 4D, 5P, 6S, 4F, 5D, 6P, 7S. Okay, you get the idea. Okay, so if I said you have to go with the lowest n plus L value and then go on to the next n plus L value, you're going to start at the first diagonal, go to the next diagonal, the next diagonal, the next diagonal. But I also said that if you have subshells with the same n plus L value, you start with the lowest n. So basically, you're going to start at the top of the diagonal and move down. So that's why, well, I'll add this. So we did a little exercise where you can take a subshell that gives you the principal energy level and the subshell type, and you can do a little addition problem and knock out an n plus L value for that subshell. In black here are the n plus L values for those subshells on those diagonals. If you're like me, you're like, are you sure? Yeah, they are. Okay. So it's a way of, when we're talking about building up, start with the ground, okay, and then go up. So I'm going to show you how this works. By the way, this is just kind of another representation of a similar thing. Okay, so let's do it with potassium, which I butchered a little bit ago. Okay, so you need a periodic table to work these, I think, because it won't say 19 electrons, it'll just say potassium, and you need to refer to your periodic table and say, oh, potassium is atomic number 19, that's how many electrons I need to find homes for. So here we go, and we're going to do it the non-hand cramp way. We're going to do spectroscopic notation. So I'll circle up there, okay, on the arrow diagram, what we're going to write down here. Down here is going to be our electron configuration. So we have 2 electrons in the 1s, so it goes like this, 1s2, okay? And then according to the arrow diagram, we're on to the second diagonal, and we're going to go 2s, and we're going to completely fill it. Now, at some point, we're going to not have to fill anymore, so we have to keep track of how many electrons we've accommodated. So the other thing when you're doing this is keep in mind the rules, and I'll kind of draw them up here. Sometimes I've seen students do it this way. We said that any S-type can accommodate 2 electrons, okay? Any P-type can accommodate 6 electrons, okay? Then we got 10 electrons for D-type. F-type is 14 electrons, okay? Just to kind of keep your wits about you. All right, so now according to our arrow diagram, we're ready for the 2p3s. But we're going to start at the 2p because it's got the same n plus L value, but 2 is smaller than 3. And we know we can put 6 electrons, and 6 added to our 4 is 10, which is clearly under 19. So I got that one. Okay, so we end up with 2p6. Another thing, and the more you do these, the more you'll be like, oh, that's interesting. So anytime you come up to like 6 electrons, you're doing these and you come up with 6 electrons in the p subshell, then actually if you look at the periodic table, you have reached a rare gas, okay? So how many electrons do we have? 2 plus 2, it's 4 plus 6 is 10. We got 10 electrons. What else has 10 electrons? Neon, okay? So actually, that's significant. That's kind of leading to, that can actually be handy. So then we continue on our arrow diagram. Looks like the 3s and 3s2 will bring us up to what, 12 electrons? Got to keep going. 3s2. Then we're ready for the p-type subshell. And if I'm at 12, right, I'm at 12, I can put 6 in a p-type, so 12 plus 6, that's 18. I'm still under my 19. You got to kind of keep an eye on that. So 3p6 looks good to me. And again, once you get to 6 electrons in a p-type subshell, you can kind of keep track of things here. We have reached another rare gas. Actually, that's argon, one of my favorites. So that's 18 electrons. We only need 1 more electron, just like you guys made sure I went back and fixed. Okay, that last electron actually is going to go in the 4s. But this is where students will want to put it in the 3d, but that doesn't have, that has a higher n plus L value. So honestly, this is the way it physically works in the electron world. It's going to go, that 1 electron is going to go in the 4s, so it's 4s1, and you're done. So, is that right? So let's do another one. Okay, and going to do a similar way. Instead of 19, we're going for 40. Okay, here we go. And one of the things about it is if we already did 19, basically what you could copy and paste. You could copy that up to 18 if you wanted to and paste it right here. It'd be the same thing. So the first 2 electrons are going to go in the 1s, so it's 1s2. The next 2 electrons in the 2s, so 2s2. The next 6 electrons in the 2p, so 2p6. And we have reached neon. The next 2 electrons are going to go to 3s, so 3s2. The next 6 electrons are going to go 3p, so 3p6. And just like before, we have reached argon. We have 18 electrons, better keep going. Our map up there says we're going to go to the 4s, just like we did with potassium. So this time we're going to go put the next 2 electrons in the 4s, so it's 4s2. Now this is where this is helpful, because now notice, where am I gonna go next? I'm gonna go to the 3D. How many electrons can I put in any D-type orbital? 10. And do I want 10?
Yep.
Yes, because I'm at what, 20 now? Okay, so I'm gonna do 3D10 to bring me up to 30. The next one is gonna be 4P. That would bring me up to 36. Okay, so 4P6. Notice I have a P6, so I could look at the periodic table, and by golly, Krypton has an atomic number of 36. So now I only need home for 4 more electrons, but next on the list is 5s, so I'm gonna have to completely fill that with 2 electrons, so it's 5s2. And now we're petering out, we only need home for 2 more electrons, but notice where they're gonna go according to the arrow diagram in the 4D. So 4D2, and that's it, man. Now this is actually, using the arrow diagram gets you in what we call the order of filling. So this is the order of filling, increasing energy level. But sometimes it's helpful to, what we say, unscramble them in the order of increasing N, principal energy level N. So that's to say, notice what needs to be scrambled is basically the difference between these 2 configurations. Okay, is we're taking, one way to think about it is we're taking the 4 and moving it over there with the other 4 and this 5 and moving it out to the end, however you want to think of that. So we're kind of unscrambling it. 40 electrons, still in the same subshells, but they're in order of increasing N. Okay? Let's do iodine. All right. Instead of 40, it's 53 electrons. So, here we go. 1s2, 2s2, 2p6. So we've reached a rare gas there, neon. 3s2, 3p6, we've reached argon. 4s2, 3d10, 4p6, we've reached the rare gas krypton. 5s2, so that brings us up to 38 electrons. Looks like we definitely still have room for 10 more, so we're going to go 4d10. Definitely have room for 36, 38, 48. Okay. Oh, nope, don't have room for 6, do we?
Nope.
Okay, good. So the next on the stop is a P subshell, 5P, but we don't need 6, we only need 5. So it's 5p5. So you know that you have the right electron configuration in a way if you add up all the superscripts and they add up to the number of electrons you're trying to find homes for. I say that, and yet that's not necessarily true. Bless you. If you have them in the wrong subshells, then it's not right. So that's it. That's in the order of filling. Now on this next slide, I kind of want to say, how are we going to unscramble those? Do you guys already have the unscrambled version? In the order of increasing N?
No, we actually had to unscramble it.
Okay, I'll tell you. Order of increasing N. It goes 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p6, 4d10, and then 5s2, 5p5. Be careful though. That last one that I've given you for these last 2 electron configurations, that's not in the order that they're added. That's just in the order of increasing N. So here's where I get to tell you, not only is this not, this is like, the box and arrow is like a lot of boxes, a lot of arrows. That's a lot of work. This can potentially be a lot of work. We can actually shorten this up by basing our electron configuration off of the last, the biggest noble gas we hit. So in this case, the biggest noble gas we hit was krypton, right? Kr. So we're going to basically, and by the way, krypton you guys had must have been right here. Does that seem right? Kr. Okay, so that's to say the abbreviated rare gas notation would simply say Kr, okay, and then to me what I would do is Kr 5s2 4d10 5p5. That's what I would do. Notice the difference down here is they're just unscrambled. Yeah. So I probably would bid Kr 5s2 4d10 5p5. Makes the most sense to me. It's the same thing. So much better. So what does the abbreviated rare gas do? How does it work? Abbreviated rare gas notation. Well, it works for the spectroscopic notation of electron configurations. And basically, you write in brackets like I said, what you're going to do is you're going to write in brackets the rare gas that's in the period before the atom you're trying to configure. So one of the things you're going to want to remember is the whole period thing, okay? So we just recently did iodine. It's in period number 5, okay? So period number 5, in period number 4, the rare gas is krypton. So that's kind of how that works. It says it can be used with the box arrow notation, but I've never seen it. All right. So, yep, one more thing. Well, a lot of things. But sometimes instead of using the box and arrow diagram to kind of find your bearings where the electrons go next, actually there's a way just to glance at the periodic table, and if you kind of know what you're doing, and I especially use this for things that don't have up to D, okay, subshells, you actually can just kind of bounce across the periodic table. So here's the deal. We need to talk about blocks. I don't think we've talked about blocks here. This block over here is the S block. What is that? It's groups 1 and 2. Okay? This block over here, that's kind of in blue here, actually is the P block, minus helium. Helium actually goes over here. So the P block, what are they? Well, they're the A group elements, groups 3 through 8. Okay? Then we have the D block. Okay? And then we have the F block. So D block are the main transition metals, and F block are the inner transition metals. Okay. So the way this works is, I must have a slide coming up. I'll put N here and N here, where N is actually N is the principal energy level that the electrons are being added. So for instance, when we finally figured out, you guys told me, okay, look at potassium. We said actually potassium peters out with 1 electron in the 4s. That's exactly where it is here. Calcium actually would be 2 electrons in the 4s subshell. Okay, let's pick on something over here. How about fluorine? Okay, again, let's see, N you can think of as actually kind of the period 2. Period 1, 2, 3, 4, etc. 6, 7. Okay, so pick on fluorine. Fluorine is actually in period 2. So here we are adding 2p electrons. Okay, so actually you count over the boxes, 1, 2, 3, 4, 5. Fluorine actually must be 5 electrons in the 2p subshell. That's exactly what it is. Okay. Now these get a little more interesting because these are actually what we say n minus 1. Okay, we're adding electrons in, instead of 4D, actually you see it's 3D, and down here it's actually n minus 2, so it gets a little more confusing. Oh, see, I already had those. I wondered where those were. Okay.
Alright, then next one, please.
So let's take a look right quick at the problems. Now, there's a problem slide at the end of this part, and I'm going to tell you which ones to do and which ones not to do. Part of this rush is because I took a few minutes to go over your test, which, I don't know, we'll just see. So the first one looks like this. You should be able to do 77. So 77, if you want to circle it, yes. Which of these following is correct? There's only one that's correct. Okay. There's something wrong with each one of those. When they're wrong, say what's wrong with them. So for instance, I mean, I don't want to do your homework, but they're kind of fun. Like, does that seem right? No, that does not seem right. Okay. Does this seem right? No. And it's not to say that this can't happen, okay, because it's a violation of Hoone's rule, but if this is the case, it's an excited state, okay? Is this right? No, that's not right. Okay, so that's pretty good. You guys can do 77. 78, similar, okay? Which of the following are correct about molybdenum? Easy for you to say. You'll find on the periodic table, its atomic number is 42. So which one of these are correct about 42? Okay. Sorry, the 42 electrons. You guys can do that one. Oops. The next one. So do the first two for sure. The next one looks like this. You are evil. Yep. Okay. Next one looks like this. You should be fine. Use what we know about how electrons are configured. It says how many unpaired electrons are, for instance, they're each a little different. There are 4, they're like A through F. There are 5, excuse me. There are 5 different little questions. And my hint here is to draw how the electrons are configured using the box and arrow notation, and it should be pretty plain to you. That's my hint. Let's see. This one, oh, so let's hold off on this one, 82. No, I think you should be able to do this one because we talked about blocks. You can do 82. My hint is feel free to, I guess I didn't finish that thought. Feel free to print this out. I'll say print and use. Because basically it wants you to write on there where those, without looking at the periodic table, this is kind of a mock periodic table, where is that element?
Oh, cool.
I think so too. 83, yes. Which one corresponds to the ground state? Which one's following the rules? Okay, and which ones are excited state? You should be able to do 83 just fine. 84. Okay, let's stop at 84. Let's stop with the rest of them. How's that? You should be able to.
So all the way to 82.
No,
will be
yeah,
83.
no, you should be able to do this one. Sorry. Don't do 84, but you can do 85 and 86. Like, that's all we talked about. You can do 85 and 86. So yes, yes, yes. I would use spectroscopic notation instead of box and arrow. So 85 and 86, yes. So not that one I said not. And this one is like the totally easiest one. So there's only one you can't do. This one basically gives you electron configuration that says which element is it. All you gotta do is count electrons. Okay, give the name of the element. I'm like, that's so funny. So which one don't you do?
84.
Okay, so not 84. Everything else is fine. All right.